Good morning, students. So, to my sorrow, this is your last laboratory work because we have scheduled to have final exam in 2 weeks. So since this is your final maybe your final laboratory work, I provided you a very simple problem. So my expectation is that all of you is taking 100 points in a limited time. So I just presume that if someone is well prepared, this problem may be solved in 10 minutes. So I'll share the handout. So in this handout, you can take a look of depth first search. So up to now, you have learned, you have practiced all the detailed data structures by yourself. But as you know, that there is a well-known structures is already implemented in your standard library. So that kind of library in C++ is called STL, which stands for Standard Template Library. Though we implemented a linked list, for example, directly, but the STL provides the list as a template class. So since it is template, you know that template can accept the type parameter. So you can make a list of integer if you'd like, and you can make a list of string if you need a list of names or something. So these are called type parameters. And STL can accept type parameters. So the adjacency list of a graph can be implemented using a list and vector types. So a simple example, for example, if you have a graph with 3 nodes, 1, 2, 3, okay, then you can make them as a vector of them. So the vector index may be used as the index 1, 2, 3, maybe the represent the nodes. And for every 3 of them is a pointer to a list. So actually a list may be linked here. So 1 is connected to 2, so 2 may be linked here. And it also connected to 3, so 3 may be linked to here. And you know that it is not here. So for 2, since this is an undirected graph, this means this a single edge means in both directions. So 1 is connected to, and 2 is connected to 1. So they are both neighbors. So in the adjacency list, 1 is adjacent to 2, so you have to connect them, connected to the second list, 1. And the same is true for 3. So 1 is also connected to 3. So in the adjacency list, you know that you have 2 edges in undirected graph. You have 4 slots to represent them. That is exactly double of each edge. So you can make this as you can call this as an adjacency list, but you know that this list may be represented of list of integer. And this is also can be represented of list of integer. And this also can be represented by list of integer. And you know that you have 3 list of integers. So you can join them with a bundle, okay, as a vector of list of integer. Okay, so the vector is useful because it is providing an index operator. So you can use freely vector 1, a vector 2, a vector 3. So this is, you have this kind of freedom. So the vector is just like an array, but it is more adaptable. So you can enlarge it dynamically, and you can control them with additional methods. So vector is very good to represent this kind of structure. So starting from first, you have to make an edge. The edge is a source and destination. That means if you have a directed edge here, this is a source and this is a destination. And in the reverse direction, then 2 is source and 1 is destination. And your graph is represented with size, which is a number of nodes. And vector list of integer, as I said before, this is represented as adjacency list. So in public, you are accepting the number of nodes and accepting a vector of edges. Since this is not, this may not be used, but the reference is used to prevent copying of edges. Since you know that this is a very large structure, so it is time consuming to copy the whole structure. So just pass the reference. And your size is initialized by n, which is the node number. And you are having an adjacency list and you are making it resize to contain enough number of nodes here. So for each edge in edges, you would like to push the source destination, which is one direction. Since this, as you know, that if you have 1, 2 as edges, and you'd like to add source, add this link first. And in the reverse direction, this is added, okay? So do you have any question up to this point? Any unclear point? No questions? Okay, good. Then I'd like to store this a little bit. Let me just, I have to, okay, so I have to delete all of them. So let me take a look of the print operation, which is naively print the adjacency list. So for each node, starting from 0 to size -1, so you are taking a list, which is an adjacency list. The ith adjacency list is referenced, and you know that the current node number is printed and the begin and. So as you know, the list is in iteration, in for the iterator only. So the list performs for the iterator only. So you have to start from the begin, and each node is, each node number is printed here with a link okay, with the link. And this is for printed for null. So and at the end, you're printing null. So it is not just null. So I'm just assuming that at the end of you have this kind of earth. So I'd like to present it as double slash. And at the end, you are returning out. So it can be used for the cases. And as you know, the default argument is set as cout. So you can just print it if cout is available. So in your main function, you have various edges. So let me drag this. Let me do this first. So you have edges from 0, 1, 0, 5, 0, 6, 1, 5, 2, 3, 2, 4, 3, 5, 6, 7, 7, 8, 7, 9, and 8, 9. Okay, so this is your graph. It is connected. Okay, so the graph, your graph will be created with 9, 10. Okay, actually 10 from 0 to 9. So you have 10 slots for the array. So let's depict this as 0, 1, 2, dot, 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 9. Okay, and 0 is connected to 1, 5, 6. So you have 5, 6. And 1 is connected to 0, 5. So it is connected to 0, 5. Okay, so in this manner, it is repeated until 9. It is connected to 7 and 8. So your output should be similar to this graph. So let me just check this with your in your Visual Studio Code. So I already have opened the Visual Studio Code here. Okay, before that, I have to save this. Maybe this is useful. Okay, maybe this is useful. So let me share my Visual Studio Code screen. Okay. So you know that you can find the same code than before. And you know that this cout is not needed because it is provided as a default parameter. So let's just execute this with learn code. Code is already running. This is a problem. So you have to I have to restart the Visual Studio Code. Okay. Let me restart it for a while. So share the screen again to here. So here you can find the execution result of them. Okay. So as depicted here, 0 is connected to 1, 5, 6, null. So 1 is connected to 0, 5, null. So you have to imagine it was deleted, but you know that you can imagine that figure. So rather than this, how about sharing all the screen? Then it is too small. Okay. So anyway, so you can depict the graph by yourself and you can check this by yourself. So let me just draw it first again. 0, 1, 5, 6, 5, 1, 2, 3, 3, 2, 4, 3, 5, 6, 7, 7, 8, 7, 9, 8, 9 here. So you can check any one of them. How about 5? It is connected 0, 1, 3. 5, 0, 1, 3 is printed here. Sorry for misspelling. How about 8? It is connected to 7, 9. 7, 9. Okay. So with this setting, you can start off here with your graph. Do you have any questions up here? No questions? Okay, good. Then I have to switch the screen to your handout again. Today's problem is depth first search. Write a program traversing a graph in depth first order. For several nodes adjacent to the current node, the visiting order of them is the increasing order of node indices. For the above graph, the sequence of nodes visited using the depth first order starting from 0 are as follows. So I have to draw them again. Okay. 0, 1, 5. Is this right? I have to take a look of the code in your Visual Studio Code. Okay. 1, 5, 6. 6 should be connected here. And 2, 3, 2, 4, 3, 5, 7, 8, 9, 8, 9. So this is your graph. So starting from 0, so let me show that how to implement that. So you have another vector of visited containing all the nodes. So you may think about that. It is recorded in each node. Okay, so you have an array of a vector of Boolean flags. So starting from 0, it is not visited. So mark this as visited and printing 0 here. And from the adjacency list, you visit 1, 5 is connected to 0. 1, 5, 6 is connected to 0. So you are assuming that 1, 5, 6. So please refer the output of the previous result. So you have to try to visit 1. It is not visited. So mark this as visited and printing 1 here. And you are going to follow the 1 is connected to 0, 5. Okay. 1 is connected to 0, 5. So starting from 1, you are trying to visit 0, but 0 is already visited, so it is not printed. So you are trying to 5. It is not visited, so you are printing 5 because of the link starting from 1. Okay, since you visited 5, you are looking for 5 here. 5 is connected 0, 1, 3. Okay, so you are trying to 0. It is already visited. 1, it is already visited. So you have to visit 3. It is not visited. So mark as visit. So print 3. So in this way, 3 is trying 2. So you are printing 2. And 2 is trying 4, 3 and 4. 3 is already visited, and 4 is not visited. So mark this as visited and print it. Okay. So you are 4 is not connected to anywhere. 2. So it is trying to 2. So it is already visited. So it is go back to 2. And this is go back to 3. And 3 is go back to 5. 5 is go back to 1. 1 is go back to 0. And 0 is trying to next one 5. So do you remember that we are starting from here? So it is trying 5. It is already visited. So 0 is trying 6. It is not visited. So mark this as, so print 6 here. So 6 is trying 0 and 7. Already visited. 0 is already visited. How about 7? It is not visited. So mark this, and 7 is printed. And as you know, the 7 is connected to 8 and 9. Okay, 6, 8, and 9, sorry. 6, 8, and 9. So the 7 is trying 6. It is already visited since it comes from there. And you are trying 8. It is not visited. So mark this and print 8. And starting from 8, you are trying 7, already visited. You are trying 9, not visited. And 9 is printed. Okay, so for 9, you are trying 7, 8, already visited, nothing to print. Go back to 8, and 8 is visiting all the neighbors. Go back to 7. 7 is visiting 6 and 8. So 7 is trying 9, but it is already visited. So 7 tried all its neighbors. Go back to 6. And 6 is trying all the neighbors, 0 and 7. So go back to 0. So it is returned from 0. Okay, then it terminates. Question. Most valid. So fourth, what is there any rule to visit any other node? Yes. So most valid is asking that 0 is connected to 3 nodes, 0, 5, 6. So in an exact manner, you can select any one of them, 1, 5, 6. But you have to visit them in this example. You have to visit them in the increasing order. So you have to visit the smallest index first. So this is your output. So any other question? So Sumin, in this graph, the graph is weakly connected graph. No, it is strongly connected. You mean that directed? Yes, yes. In a directed manner, you may consider this strongly connected components, okay? So this is a directed graph. So you have to add two links for that. So if you don't have any question, I'd like to explain your program input and output. Your program should read from standard input. The first line of the input contains n and k. N is the number of nodes, and k is number of edges, respectively. The nodes are indexed from 0 to n-1. Each of the following k lines contains an edge information, source and target, is given. S and T denotes the indices of the source and target of a node, target nodes, okay? So naturally, S is greater than 0, S and T is greater than or equal to 0, and should be less than n. But I'd like to make it order S is less than T, okay, to make it explicit, to help you on increasing order, to process it in an increasing order. And the last line contains an integer b, the index of the starting node. So you started from 0, but you can start anywhere of the graph, okay? So the starting node is indexed as b. Your program should print a sequence of nodes visited in depth first order traversal. So to facilitate your printing, so print a single node in a line. Okay, so it is more convenient to print it. So since you can print the new line as a delimiter. And for additional requirement for bonus point, your program should have less than 3 issues of the code quality. So let's take a look of another example. So let me save this and delete all of them. This is your first example. For this, I'm using the same graph. So let me show them. So it consists of 7 nodes, and 0 is connected to 1 and 5. And 1 is connected to 5, and 2 is connected to 5, and 1 is connected to 6, and 4 is connected to 5. So you may think that 3 is missing, okay? So 3 is isolated. So this is not a connected graph, okay? But for the depth first traversal, you are starting from 5. So 5 is the source. So starting from 5, you know that the 5 is connected to 4 nodes. So which one is the minimum? 0. So 5 should be printed since it is not visited. And you are trying to visit 0. So since 0 is not marked, okay, so 0 is printed. So starting from 0, it is connected to 1 and 5. So which one is the least one? 1. Okay, so you have to mark this. It is since it is not visited. And starting from 1, it is connected to 5 and 6. And as you know, the 5 is already visited. So you're trying 6. 6 is not visited, so print is 6. And the 5 and so starting from 6, you are trying to 1. It is already visited. Okay, so nothing to do in 6. So go back to 1. And 1 is trying 5 and 6, 0 and 5 and 6. Okay, so I just omitting explaining 0 in the first explanation. Sorry for that. So it is trying 3 of them. So go back to 0. So 0 is trying the next one, which is 5. It is already visited. Go back to 5. Okay. And 5 is trying 1, which is the next one, but it is already visited. So 5 is trying 2. So 2 is not, since 2 is not visited, 2 is printed here. And starting from 2, you're trying 5, already visited. Nothing to do, go back to 5. And you know that 3 of the edges are tried already. So 5 is selecting another edge, 4. So 4 is, since 4 is not visited, visit here, 4. Okay. And 4 is trying to 5, which is already visited, and go back to 5. Okay. So 5 is trying all of them. So this is the end of depth first traversal. Okay. So as another starting point, so let me just change the color. Orange one. So starting from 1, so 1, since 1 is not visited, you are marking this as 1, and 1 is printed. And as you know, 1 is connected to 0, 5, 6. So you are trying 0 first. Since it is not visited, you mark this as visited and print 0. And starting from 0, 1 and 5 is connected, and 0 is trying 1, it is visited. 0 is trying 5, since it is not visited, you mark this as visited. 5 is printed here. And starting from 5, 5 is trying 0, already visited, 1, already visited, so 2 is tried. So 2 is not visited, mark 2, and 2 is printed here. And starting from 2, it is trying 5, already visited, so go back to 5, since all the edges will be visited from 2. And from 5, it is already go back from 2, it is trying 4. Okay, not visited, print 4 here. Since 5 is tried all the nodes, so it is go back to where? It is from 0 or 1. I think it's from 0. So go back to 0. Since 0 is trying all the things, so it is go back to 1. So 1 is trying 0 and 5. Okay, so it is trying 6. The last one, not visited, 6 is printed here. Okay, from 6, it is trying 1, visited, so go back to 1. So 1 is trying 0, 5, 6, all the linked nodes, connected nodes are tried, so it ends. So this is the depth first order traversal starting from 1. Any questions? No questions? And you are about 30 minutes to go. No questions? Then please try this. When was the deadline? Tomorrow night. Okay, so the deadline is 9 a.m. tomorrow, as usual. So please try this problem because it is really simple. Okay, just maintaining the flag vector, and then everything can be done with a simple recursion. Okay, so if you don't have any questions, let's call this a day. Bye-bye.